Welcome to our introduction to programming. In this lecture, we are going to build a story about what computers are, how they help us solve problems, and how people create useful systems with them. We will begin with the history of computing, then examine the role computers play in daily life. From there, we will develop a problem-solving mindset using input, process, and output, followed by 4 ideas in computational thinking. We will also consider programming as a creative activity, look at the digital artifacts that code produces, and discuss why collaboration matters. Finally, we will connect these ideas to the information system development lifecycle. The goal is not simply to memorize terms. The goal is to see programming as a disciplined way to frame problems, design processes, build artifacts, and learn from results. Computing from Switches to Solutions by the Programming Professor. Here is our roadmap for the lecture. We begin with a brief history, moving from early switching systems to the information age. Next, we look at computers around us, including the embedded computers that are easy to overlook because they live inside other devices. We then focus on computational problem solving and the 4 moves of computational thinking. After that, we will discuss the creative process and the computational artifacts that result from it. The final part of the lecture emphasizes collaboration, data science, and information system development. Notice the progression. We move from the technology itself to the way we think, to the way people work together to create systems. Keep this outline in mind because each section adds another part to the same central question. How do we turn a problem into a useful result? Computing began with a very simple idea. An on or off switch can represent 1 or 0. Early computers assembled thousands of these switches into machines that occupied entire rooms. As engineers learned to make switches smaller, computers moved from rooms to chips, from chips to coin-sized devices, and eventually into objects far smaller than a pinhead. This history matters because it shows how a small improvement, repeated many times, can completely change what is possible. The graph illustrates Moore's law as a pattern of exponential decay in switch size. Every few years, the basic component becomes roughly half as large. The result is not merely a smaller machine. Smaller switches reduce cost, power consumption, and physical space, allowing computation to spread into more parts of society. The next historical step is the information age, which is still unfolding. For thousands of years, most people lived within an agricultural economy. The industrial age then transformed production, transportation, cities, public health, and population growth. The information age adds another transformation by shifting human activity toward creating, managing, and using computerized information. The graphic uses a rising population curve to emphasize that social change accelerates after industrialization and continues into the information age. This does not mean that every change is automatically positive or that technology determines our future by itself. It means that computing has become a major environment for work, learning, communication, and entertainment. Since the 1990s, networked information has changed everyday behavior, and the full consequences of that change are still being worked out. The phrase computer once suggested a large, expensive machine located in a government office, a business, or a research laboratory. Today, computing is distributed across desktops, laptops, tablets, and smartphones. More importantly, computers are embedded inside cars, televisions, printers, thermostats, satellites, and many other electrical devices. An embedded computer may be invisible to the person using the larger product, but it still receives data, follows instructions, and produces actions or information. This shift changes how we think about programming. We are not only writing applications that someone opens directly. We may be building the control system for a vehicle, the interface on a thermostat, or the software that helps a device respond safely. As you look around your own day, ask yourself where you encountered a computer before class. At the center of computational problem solving is a simple loop: input, process, and output. A computer receives data from a person, a sensor, a file, or another system. It then applies instructions to that data. Finally, it displays an answer, stores a result, or produces an action. The example on this slide asks whether the number 25 is prime. The input is the number. The process tests whether it can be divided evenly by other numbers. The output reports the conclusion. The loop is useful because it gives us a clear way to describe almost any program. When a program behaves incorrectly, we can ask which part of the loop is wrong. Did we collect the wrong input? Did the process contain an error? Did we produce the wrong output or present it unclearly? Computational thinking gives us 4 complementary moves. Decomposition means breaking a difficult problem into smaller questions that we can address one at a time. Pattern recognition means looking for repeated structure, useful similarities, or shortcuts. Algorithms are organized sequences of instructions that describe how to complete a task. Abstraction means finding a general idea that can be reused across many specific situations. These moves are not limited to professional programmers. We use them when planning a trip, organizing information, or troubleshooting a device. In programming, however, they become especially important because a computer needs the problem stated with enough precision to execute it. Together, the 4 moves help us transform a vague challenge into a process that can be represented with data, instructions, and decisions. This slide demonstrates how an algorithm can be expressed as pseudocode. The example tests whether a number is prime by checking possible divisors. The purpose of the pseudocode is not to teach a particular programming language. Instead, it gives us a precise, readable plan that can later be translated into Python, Java, C, or another language. The algorithm begins by receiving a number and assuming it is prime. It then examines divisors one at a time. If a divisor works evenly, the process can stop early because the number is not prime. If no divisor works, the number is prime. This example shows decomposition through repeated divisibility questions, pattern recognition through the early stopping rule, and abstraction because the method can be applied to any positive number greater than 1. Pseudocode helps us reason before syntax gets in the way. Programming is often described as technical, but it is also a creative process. A programmer makes choices about structure, language, interface, visual presentation, efficiency, and user experience. Those choices shape the artifact that other people encounter. The graphic shows a cycle from an idea to a set of choices, then to an artifact, and finally to feedback that can inspire a new idea. 2 people can produce the same general result through different processes. One process may be faster, clearer, easier to maintain, or more accessible than another. Even when the result must meet strict requirements, there is room for creativity in how we reach it. Correctness is essential, but it is the beginning of good programming rather than the entire definition. Thoughtful programmers also ask whether their design is understandable, useful, adaptable, and appropriate for its audience. Code becomes a computational artifact when it is combined with data and used to produce something people can experience or operate. Artifacts may be digital, such as audio, images, video, documents, games, and applications, or they may be physical objects controlled by software. The process begins with a practical need or a creative goal. Code and data are then used to create an artifact that can be copied, edited, and shared. Digital artifacts are especially flexible because changes can be made quickly and distributed widely, without rebuilding the physical object each time. That flexibility also creates responsibilities. We need to consider accuracy, security, privacy, accessibility, and the effects of sharing. A program is not just text stored in a file. It is part of an artifact that can influence how people work, communicate, make decisions, or express ideas. Bigger computational problems usually require more than one perspective. Collaboration brings complementary strengths, faster feedback, and shared ownership of a complex artifact. One person may understand the user's needs, another may design the interface, and another may focus on testing or performance. Communication tools extend this collaboration across physical distance. Instant messaging and shared documents support discussion, while version control helps a team review changes, synchronize code, and recover earlier versions. Open source software makes this process especially visible because a community can maintain and improve a shared artifact over time. Collaboration does not simply mean adding more people to a project. It requires clear communication, agreement about goals, and ways to manage differences. A strong team combines individual expertise while keeping the shared problem and the people affected by the solution in view. Data science shows how collaboration can connect people, institutions, and computing. The Million Veteran Program is an example in which veterans, hospitals, universities, government agencies, and industry contribute different kinds of expertise. Participants provide consent, information is stored securely, and researchers analyze the data to look for patterns that may improve understanding of disease. The important lesson is that data does not produce insight automatically. People must decide what to collect, how to protect it, how to analyze it, and how to interpret the results. Ethical requirements are part of the technical work. Privacy and consent cannot be added after the analysis is complete. In modern programming and computing, responsible practice includes asking who benefits, who may be harmed, what assumptions are being made, and whether the people represented in the data have been treated with respect. The system development lifecycle gives us a structured way to move from a problem to a working system. Analysis identifies goals and requirements. Design determines how the system should be built. Implementation creates the system, and testing checks whether it works and satisfies the requirements. The slide contrasts two ways to organize these phases. In a waterfall process, the phases are completed in sequence, with one major pass through the life cycle. In a spiral process, the phases are repeated, allowing each cycle to become more detailed and more informed by feedback. Neither diagram is simply a set of vocabulary words. Each represents a different way to manage uncertainty. When requirements are stable and changes are expensive, a sequential approach may be useful. When users need to see prototypes and provide feedback, repeated cycles can reveal problems earlier. Consider a small system for a school with 80 students. The system must allow students to register for classes, send email, and submit classwork. Even this modest example benefits from a development process. The team first asks students and teachers what they need. It then sketches the workflow and the data, builds a usable first version, and tests that version with realistic tasks. The code shown on the slide represents the idea of a development loop rather than a complete program. A team analyzes feedback, refines the design, implements a small change, and tests the result. After deployment, the work continues because users discover bugs, misunderstandings, and new needs. Maintenance is not a sign that the original team failed. It is a normal part of building systems that operate in a changing environment. The people around the code are part of the system development process. Developers build and connect the technical pieces, but other roles contribute essential knowledge. Product managers learn what clients and users need and help shape goals. User experience engineers focus on making systems understandable, usable, and accessible. Quality assurance engineers design tests that expose failures before users depend on the system. Technical support specialists help users solve problems and often discover patterns that should inform future improvements. Project managers coordinate schedules, milestones, and communication across the work. These roles overlap, and the exact titles may differ from one organization to another. The larger point is that good systems are socio-technical. Requirements, usability, quality, support, schedules, and code must meet. A programmer who understands this wider collaboration can design more useful and responsible solutions. Let us bring the lecture together with the programmer's mindset. Computing has grown from physical switches into an invisible layer of everyday life. A computer takes input, applies a process, and produces output. Computational thinking helps us decompose problems, recognize patterns, write algorithms, and use abstraction. Programming is also creative because choices shape the artifacts and experiences people receive. Collaboration and data allow computing projects to operate at a scale no individual could manage alone. Finally, the system development lifecycle reminds us that useful systems are built through analysis, design, implementation, testing, feedback, and maintenance. As you begin your own programming work, practice describing every problem in terms of data, process, and output. Then ask which people, assumptions, and consequences belong around that technical description. That is the foundation for programming with both skill and judgment. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.